Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is invertibility of matrices, where we talk about four necessary and sufficient conditions for a matrix to be invertible. It's what I call the Short-Long Theorem. But before we start, I would like to tell you what other things you need to know, the prerequisites for this video. All of these are subjects of other videos that you should watch before seeing this one. If A is an n by n matrix, a square matrix, then you need to know what does it mean to say A is invertible. Basically, all that means is that there's some other square matrix B such that A times B and B times A are the identity matrix. The identity matrix being the matrix which has one down the diagonal and zeros everywhere else. The special thing about the identity matrix is that when you multiply it by other matrices, nothing happens and you get that other matrix back. You also need to know what row equivalence means. There are three types of elementary row operations: multiplying a row by non-zero constant, switching two rows, adding a multiple of another row to a given row. And when I say A is row equivalent to identity, it means that you use those elementary row operations and eventually get identity. Some matrices you can do that, some matrices you cannot. You also need to know that if you look at a matrix equation of the form AX equals B, then you're talking about a system of linear equations. X is a column vector of unknowns, B is the right-hand side vector, and A is your coefficient matrix. And in the case where the matrix n by n, then that means you have n equations and n unknowns. The number of equations and unknowns is the same. Ax equals b is a system of linear equations regardless of whether or not A is a square matrix or not. But the number of equations and unknowns might vary depending on the size of the matrix. Again, there was a whole video on that. You also need to know what an elementary matrix is. An elementary matrix, briefly, is a matrix that you get from the identity matrix by doing one elementary row operation. And the purpose of an elementary matrix is that if you pre-multiply a matrix by an elementary matrix, then it does that elementary row operation for you. So instead of doing elementary row operations, you can multiply by elementary matrices. And you need to know that elementary matrices are invertible, and the inverse of an elementary matrix is also an elementary matrix. Again, there was a whole video on elementary matrices. You also need to know that if you multiply two invertible matrices, two matrices that have inverses, the product is also invertible. You also need to know how we solve a system of linear equations using elementary row operations. You start with an augmented matrix, you do elementary row operations, you get a reduced row echelon form, and then you look at basic and non-basic variables. If you have a row of zeros in your coefficient matrix, but the last column has something else, then the system does not have any solutions. Otherwise, it does. You need to know what leading ones are, basic variables and non-basic variables are when we solve a system of equations. Non-basic variables are the ones that in their column, there's no leading one, and they're the ones that are free variables. They're the ones that you can call anything you like, and then you solve the basic variables in terms of them. So these are the things that, again, if you don't know what they are, then watch a previous video. Otherwise, we're ready to go. So here's the theorem that the main object of this lecture. So I have an n by n matrix, and I have an n by one column of unknowns, vector of unknowns. So x is not just a number or just one variable. It's something like x, y, z, w, if n was 4. And then I'm going to say the following statements are equivalent. I'm not saying that any one of these things are true or false. I'm going to tell you a bunch of statements that the truth or falseness goes together. They fall or rise together. Either all of them are true or all of them are false. I will say a word about that, what the following statements are equivalent means in the next slide. So what are they? One is that A is invertible. So then one nice thing about this theorem is that its actual hypothesis to begin with is nothing. A is just an n by n matrix. But it's telling you not that all matrices are invertible, but it's telling you conditions that are equivalent to being invertible. So it's giving you alternate definitions, if you will, for being invertible, or sufficient and necessary conditions for being invertible. So one condition is A is invertible, meaning that it has an inverse. There's some other matrix that you multiply and you get identity. And we would like to know which matrices are invertible, and this theorem is going to help us do that. So the other condition that equivalent to that is that the only solution to AX equals 0. Now, AX equals 0 is a homogeneous system of linear equations. As we said, AX equals B is a system of linear equations, but here the right-hand side is all zeros. If you have a homogeneous system, when the right-hand side, the constants are all zeros, then x equals 0 is always a solution. You can put all the variables equal 0 and you get a solution. That's not the point. The point here is that we're talking about the situation when that's the only solution. The x equals 0 is the only solution to x equals 0. So what? Is it or is it not? It could be or could not be. But if A is invertible, then the only solution would be x equals 0. If the only solution of x equals 0 is x equals 0, then A is invertible. So that's the second statement. The third statement is that A is row equivalent to identity, meaning that if you start with A and do elementary row operations, you will eventually, if you do it right, you will get to identity. And the fourth one is that A is the product of elementary matrices. I will say a word about equivalence of these things. Then we will talk about how to prove this theorem. But the nice thing about this theorem is that it's connecting various things together. It's connecting elementary matrices to homogeneous systems, to invertibility, to row equivalence. So all of these things are now related according to this theorem, meaning that if you know one of them, then you know the other ones. And that's very helpful because each one of these is slightly different. And in different situations, you might want to use different ones of them. Like, for example, the third one, being row equivalent to identity, is the easiest one to actually do. Like, in the sense that if a matrix walks through the door, I want to know if it's invertible or not. I can just do elementary row operations, see if I get identity or not. That's a pretty straightforward thing. And what this theorem tells me is that doing that can tell me if the matrix is invertible or not. I should say one other thing. Why do I call it the short-long theorem? Other people don't call that the short-long theorem, often called the master theorem, or at least a bigger version of it is called the master theorem. I call it the short-long theorem is because this theorem is growing. It's getting longer as we speak. In the future lectures, we will see other conditions that we're going to add to this theorem that are equivalent to these. As we develop more tools, we will add more conditions to this theorem. And eventually, it'll become quite a long theorem, which I will call the long theorem. And that long theorem is what other people might call the master theorem for matrices. And this is the short version of the long theorem. So it's the short-long theorem. Equivalent mathematical statements. What do I mean that? I'm not saying any of them are true or false. So I'm not saying A is invertible. I'm not saying it's row equivalent to identity. I'm not saying x equals 0 has only one solution, x equals 0. And I'm not saying A is a product of elementary matrices. So what am I saying? What I'm saying is that if one of them is true, then all are. Then they all are. They fall or rise together, sort of like a union kind of thing. If one is false, then so are the rest. Instead of saying it that way, I could have said a lot of if and only if statements. I could have said A is invertible if and only if x equals 0 has only one solution, and that's x equals 0. I could have said A is a product of elementary matrices if and only if A is row equivalent to identity. I could have said a lot of if and only ifs, but it's much more efficient to just put them all in as they're all equivalent statements. What do I have to prove? Because they are a bunch of if and only ifs, I have to prove actually lots of things on the face of it, because each of these has a different hypothesis and a different conclusion. For example, I have to prove that if A is a product of elementary matrices, then x equals 0 has only one solution, and that's x equals 0. I also have to prove that if A is invertible, then it's row equivalent to identity. Each one of these conclusions has a different hypothesis, so I can't rely on the other ones. I have to start over again. Here's my hypothesis. Here's what the conclusion is. I have to do a lot of different proofs. And how many proofs? Well, there are a lot of them. There are 4 statements, so for each one of them, I've got to prove 3 other ones. So that's 4 times 3, 12. And if you don't think about it too much, you might think that, okay, I also have to prove that if one of them is false, then all the other ones are false. That would make 24 statements. However, all we're going to do is prove that the statement 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies back 1. Now, why is that enough? Because if I prove statement 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1, then I've proved that all of them are equivalent. So why? For example, if I know 1 is true, then how do I know 4 is true? I didn't prove that directly, but all I proved is that if I know 1 is true, then 2 is true. But I also proved that if 2 is true, 3 is true, and if 3 is true, 4 is true. So 1 implies 2, 2 implies 3, and 3 implies 4. So I've got 4. If I know 4, how do I know 3 is true? Well, 4 implies 1, 1 implies 2, 2 implies 3. If I know 3 is false, how do I know 4 is false? Well, if 3 is false, you might say, well, maybe 4 is true. But if 4 is true, then 1 is true. And if 1 is true, 2 is true. And if 2 is true, 3 is true. But 3 was false. So that there is a contradiction. So 4 could not have been true. It must have been false as well. So if I prove these 4 implications, I've proved that all 24 statements, that if any one of these statements is true, then so are all the other ones. If any one of them is false, then so are all the other ones as well. For each proof, you've got to make sure that you know what the assumptions are and what the conclusions are. And the proofs matter. The proofs matter because they're giving you ways of thinking about things and ways of arguing. And those arguments actually are going to come in handy much more than anything else. Actually, this theorem, the statement is useful too, often, but you actually want to use the arguments also. So you want to pay attention to the arguments. And to do that, you've got to know what the assumptions are, which for each part is going to be different, and what the conclusion are, which again, for each part is going to be different. And again, this is an important theorem because it characterizes invertibility. Any one of those conditions could actually be taken as a definition of invertibility if you want. Let's get on with the proof. The matrix walks through the door, it's a square matrix. I know it's invertible. That's what I'm given. That's my hypothesis. I know that I have an invertible matrix, but now I want to solve AX equals 0, which is a homogeneous system of linear equations. It's homogeneous because the right-hand side is all zeros. And I want to prove to you that x equals 0 is the only solution. The fact that x equals 0 is a solution is not a big deal. That's certainly true. But why is there are no other solutions? And so let's get started. So we're assuming A is invertible, and we want to show that the system of linear equations AX equals 0 has only one solution, namely x equals 0. Whenever you're doing a proof, you want to be clear about what the assumption is and what the conclusion is, and set that up and know so that you know when you're done. And that sort of knowing the structure of the proof is helpful. So I'm going to start with AX equals 0 and show you that x must be 0. So A is invertible. So that means that there's some matrix called A inverse, that if I multiply by A, I get identity matrix. Okay, so now I start with AX equals 0. What am I going to do? What I'm going to do is I'm going to multiply on the left by A inverse. So I'm going to say, what's A inverse times AX? Well, A inverse times AX is going to be the same as A inverse times 0. Why? Well, because AX is 0. So instead of AX plus 0, and you get A inverse times 0. Now, this 0 is the column vector 0. Why is that? Well, when you say AX equals 0, A is n by n, x is n by 1. So AX is n by 1, and 0 must be n by 1. So this is a column vector of zeros. And if you take a matrix and multiply it by a column vector of zeros, you take the rows and dot product with all zeros, you get 0. So you get the 0 vector. So what you got is that A inverse AX is the 0 vector. Now hold that thought, and let's look at A inverse AX again. A inverse AX, I can use the fact that matrix multiplication is associative. It's not commutative. AB is not the same as BA always. Sometimes it is, but often it's not. But A times BC is the same as AB times C. It's associative. So I can switch those parentheses and I get A inverse A times X. I did that because I know what A inverse A is. It's the identity matrix. And I know that identity times X is always X. So A inverse AX is really X. But A inverse AX was 0 in the previous line. So X must be 0. So this means that if you start with AX equals 0, you have no choice, no options along the way. X will be 0. X will be the 0 vector. So we're done. We started with assuming that A is invertible. We proved that AX equals 0 has only one solution, namely X equals 0. How did we prove that? We said that, okay, if you have AX equals 0, then you must have that X is 0. So that was 1 implies 2, 1 out of 4 gone. So now 2 implies 0. This time, I don't know anything about invertibility. Still a matrix walks through the door, still square. But what I know now is that if I try to solve the system AX equals 0, this homogeneous system of linear n equations and unknowns, then that has one solution and one solution only, and that's X equals 0. And I want to prove that reduced row echelon form of A is the identity matrix. So assuming that the only solution to X equals 0, I'm repeating myself, is X equals 0, I want to show that A is row equivalent to identities, which means that the reduced row echelon form of A is identity. If you do elementary row operations to A, you can get to identity. So let's see how that works. So I'm going to say something. I'm going to say that take the augmented matrix. To solve AX equals 0, what do? We're going to do a thought experiment. How do we solve AX equals 0? The way you're going to solve AX equals 0, you're going to find reduced row echelon form of the augmented matrix. You take the matrix A, you append the right-hand side to it. In this case, is all zeros, so it's a column of zeros, and you find the reduced row echelon form of that. Now, either that reduced echelon form has a row of zeros or it doesn't. I'm not saying anything profound. I either wear a hat or I don't. I either have $100 in my pocket or I don't. I'm not eliminating any possibilities. That reduced row echelon form either has a row of zeros or it doesn't. And because the second column is all zeros, it's actually going to be the whole augmented matrix after doing reduced echelon form will have zero, not just the A part. Now, if it has a row of zeros, then it has fewer than n leading ones, or what are called sometimes pivots. Why is that? Well, because A is n by n. And so if it has n rows and one row has all zeros, that row or more rows, those rows do not have any leading ones. So the number of leading ones is less than n. But that means that some column doesn't have a leading one either, some column of A. I mean, the right-hand side never has a leading one, but the column of A, there was n of them, and if there's fewer than n leading ones, there's not enough to go around. One of them, at least one of them, does not have a leading one. So that means that there is that corresponding variable is a non-basic variable. So if you remember how you solve systems of equations, when you have a column with non-leading one, you say that that's a non-basic variable, that's a free variable, that's a variable that can be anything you like, and then you can solve for basic variables in terms of that. And then, so that non-basic variable can take on any value, which means that because you can solve everything else in terms of them, there are going to be infinite number of solutions. But was not supposed to be the case. Our assumption was that AX equals 0 has just one solution. So this means that the reduced echelon form can't have a row of 0. So we're in the other case. It doesn't have a row of zeros. But if it doesn't have any row of zeros, then what can I say? Well, in that case, that means that it has n leading ones. Every row has a leading one, and every column has a leading one. But in every column that is a leading one, other than that leading one, everything else is 0. So, and the leading ones are staggered. That's what a reduced row echelon form is. So that means that the reduced row echelon form of the augmented matrix must be the identity appended with 0, which means that that column of zeros, that augmented part, doesn't really do anything. That was just sitting there all along. So that means that the reduced row echelon form of the matrix A must be identity, and we're done with our proof. If you start with AX equals 0 and you know that the solution is just 0, it must have been that when you were solving it and you reduced it, you got identity on this side. If you got anything else, you would have had an infinite number of solutions. You can't have 0 solutions because this is a homogeneous system, and x equals 0 is always a solution. So that was proving that 2 implies 3. Okay, now let's prove that 3 implies 4. Now again, our hypothesis changed. This time, I don't know anything about invertibility. I don't know anything about AX equals 0. But what I do know, again, I do know that an n by n matrix walked through the door, but I know that it's row equivalent to identity. I know that if I start with A and do elementary row operations, I can get identity. I want to show you that it's a product of elementary matrices. And again, what's an elementary matrix? Is a matrix that you get from identity by doing an elementary row operation. So I do know that A is row equivalent to identity, and I want to show you that I can get from A to identity via elementary row operations. Now, instead of doing an elementary row operation, we can multiply by elementary matrix. That's the reason for being of elementary matrices. That's why they live. Their job in the world is to do elementary row operations for you. If you pre-multiply a matrix by an elementary matrix, it does one elementary row operation for you. Which one? The one that you did to identity to get it. So if I can do a bunch of, if A is row equivalent to identity, then that means that I have a whole bunch of matrices, elementary matrices E1 through EK, that if I multiply by A, one after the other, eventually I get identity. This is just the same as saying that it's row equivalent to identity. So I'm starting with A, then first I'm multiplying by E1. So E1 is the first elementary row operation I do. Then I do multiply by E2, that gives me another elementary row operation and so forth. And finally EK. So there's K elementary row operations I did, but I didn't actually do them. I just multiplied by elementary matrices, which is the same thing. And I got identity. That's my hypothesis, that I can do this. All right. Now, why does that make it A is a product of elementary matrices? Well, I'll start with here, and I will peel off the elementary matrices and move them to the other side. And I do that by multiplying by inverses. So I'm going to multiply by the inverse of EK first. That last elementary operation I did, I'm going to undo that first. And I can do that because I know that every elementary matrix is invertible. And so multiplying by EK minus 1 on the left, you have to say on the left or right because matrix multiplication is not commutative, so it matters. So if you multiply on the left, you get EK inverse times EK minus 1 all the way to E1A equals EK inverse times identity. Why? Well, because EK minus 1 all the way to E1A is identity. And so EK minus 1 times that is going to be the same thing. But when you do that multiplication on the left, that EK minus 1 times EK gives you identity. And that identity times everything else is just that everything else. And so you really have got EK minus 1 times EK minus 2 all the way to E2, E1 equals EK minus 1. So now you have peeled off one of those EKs. So what this says is that if you do fewer elementary operations on A, one fewer, then what you're going to get is not identity, but the inverse of that last one you were going to do. I mean, that's sort of if you want to read it, but you don't have to read it. This is this equation is what it says. And I'm going to repeat that. This time I'm going to multiply by the inverse of EK minus 1, again on the left. I guess again on the left, because you're saying the opposite of me. And so what I will get is that EK minus 2 times all the way till E2, E1A equals EK minus 1 inverse times EK inverse. And when I'm done, I will eventually get that A is E1 inverse times E2 inverse all the way till EK minus 1 inverse. Note that the order of the E's switched. It used to be EK times EK minus 1 times E1. Now it's E1 1 inverse, E2 inverse all the way to EK minus 1. And you can't switch it around. So I got A is a product of these things. I'm not quite done because I said A is a product of elementary matrices, not the inverses of elementary matrices. But now I remember from my video on elementary matrices that inverses of elementary matrices are also elementary. So are elementary matrices. So those E1 inverses and E2 inverse, EK inverses are all elementary matrices. And I wrote you A as a product of elementary matrices. So I'm done with that. So only one other one left. Now I've got to go back again. The hypothesis changed, the conclusion changed. This time I know that A is a product of elementary matrices. And I want to prove to you that A is invertible. But one thing I do know is that elementary matrices themselves are invertible. And I also know that product of invertible matrices are invertible. If you take two matrices and invertible, multiply them, you get an invertible matrix. If you take three matrices that are invertible and multiply them, you still get invertible because the first two multiplied is invertible, then you have an invertible times invertible, that's invertible. So product of invertible matrices are invertible, and elementary matrices are invertible, then of course, then if A is a product of elementary matrices, A will be invertible because it will be a product of invertible matrices. And we're done. So this last one was pretty straightforward. Now, we proved the theorem. And again, now I want to give you some conclusions. The first thing I want to tell you is a corollary of the proof, like something that we did in the argument that's actually helpful to say. If you start with an n by n matrix and do elementary row operations and find its reduced echelon form, then we said you get a row of zeros or you don't. If you don't get a row of zeros, what we said is when you have n leading ones and you get the identity matrix. But if A is, and that's when we proved that that's when A is invertible. But if A is not invertible, that's not what you're going to get. And the only thing you're going to get is a matrix, a row equivalent to a matrix with a row of zeros. So if A is not invertible, you have to get a row of zeros, because if you didn't get a row of zeros, you would get identity. And that would mean that A is invertible by the Short-Long Theorem that we proved. On the other hand, if A is row equivalent to a matrix with a row of zeros, it's not going to be a row equivalent with identity, and so it's not invertible. So this is an if and only if statement. It follows from the theorem we did, but it's actually from the argument was in the proof, and I wanted to bring that out because it's a useful thing to keep in mind. As a sort of a small application of the Short-Long Theorem, we shall see many applications. I want to prove the following. When we say A is the inverse of B, then we have, by our definition, was that AB's identity and BA's identity, that we said both of those. I want to tell you now that we actually don't need both of those. If you know one, the other one automatically follows. So here's the theorem that says that. Two matrices walk through the door. They're n by n matrices. One of them claims that it's the inverse of the other. Now, up before this theorem, a priori, I say, well, if I want to check that, I've got to multiply AB, I've got to multiply BA, see both of those are identity, then I trust what you guys are saying. This theorem says that assume that you just did B times A, and that was identity. Then B is A inverse, meaning that the other one is also true, that AB is also identity, and you don't have to check it. So this says that if you just check one of them, it's fine, then you don't need to check the other one. Okay, now why is that? Why is that? So when you say B is A inverse, you mean that the other one, AB, is also identity. And so if you know one, you know the other. So let's try to prove that. So BA is identity, and I'm trying to prove to you that B is A inverse. But I'm going to do it in two steps. First, I'm going to prove that A is invertible. Maybe B is not its inverse, but it's invertible. So these two matrices walk through the door, A and B, n by n matrices. All I know is BA is identity. For all I know, neither one of them has an inverse, leave alone being each other's inverses. So the first thing I'm going to prove is that the A guy is invertible. And how am I going to do that? Well, how do you prove something is invertible? Well, you could find an inverse for it. Oh, but we have the short-long theorem. That means we don't have to do that. We can do any one of our four things. And what I'm going to do is that I'm going to say, let's look at AX equals 0. So that's a system. A is a matrix. If I want, I can make a system of linear equations, a homogeneous one. And I'm going to try to see if I know anything about its solutions. If I can somehow, by hook or crook, convince you that the only solution to this is x equals 0, then we know A is invertible. We don't yet know that B is the inverse, but we know A is invertible. So start with AX equals 0. And what I'm going to do is multiply on the left by B. B times AX is going to be the same as B times 0. Why? Well, because AX is 0. And B times 0, 0 is the column vector of zeros, is 0. So B times AX is 0. But on the other hand, B times AX is, you can switch the parentheses because, again, matrix multiplication is associative. So instead of B times AX, you can write BA times X, and BA is identity, because that's what we assume, that B times A is identity. And then identity times X is X. So B times AX is really X, and we just showed X is 0. So I just showed you that X equals 0 has one solution, and that has to be X equals 0. Because if you start with AX equals 0, you get that X is 0. So that tells me that A is invertible. Okay, so what? But now I want to show you that B is the A's inverse. It's not just A is invertible, but this guy B, this specific B is invertible, it's the inverse. I had BA equals identity. I know A is invertible. So somewhere in the world, there is a matrix called A inverse. Maybe it's B, maybe it's not. But there is some matrix A inverse. So I'm going to take that matrix and multiply it on the right. And so what I will get is that BA times A inverse is identity times A inverse. Okay. So, BA is identity. So BA times A inverse is going to be the same as identity times A inverse. But what's identity times A inverse? That's A inverse. What is BA times A inverse? Again, use associativity. Switch the parentheses. I'm not using commutativity. I'm using associativity, and I get B times A inverse, and that's going to be B, because A times A inverse is identity, and B times identity is B. So I'm getting B is A inverse, and that's what I wanted to prove. B is A inverse. So we're done with that. So let me just recap the short-long theorem. It says that a matrix walks through the door. It's a square matrix. Then and you have an n by 1 column vector of unknowns. Then the following statements are equivalent. So none of these are true. None of them are false. But if one is true, all of them are true. If one of them is false, all of them are false. One is A is invertible. Again, what that means is that there's some other matrix B such that AB is identity. And we just saw that that also means BA is identity. The other one is about systems of linear equations, that if you try to solve the system AX equals 0, you'll get just exactly one solution, the trivial solution X equals 0. So one way to say this is that AX equals 0 only has the trivial solution. Also, A is row equivalent to identity, meaning that if you start with A and do elementary row operations, you should get identity. This is actually the way we were going to find inverses, by doing that. Because if you do these elementary row operations and you get identity, that's an easy thing to do. You'll know if it's invertible or not. And we will think about that a little bit more in a future lecture, in the next lecture, actually, to see how to make that into finding the inverse. And finally, A is a product of elementary matrices. Now, this is also, the last one is also interesting, because in the lecture on elementary matrices, we said that elementary matrices are invertible. And we also know product of elementary matrices are invertible. What we just proved is that all invertible matrices are product of elementary matrices. And therefore, if your day job is finding invertible matrices, all you have to do is find product of elementary matrices. Not only you will get invertible matrices, you will get all invertible matrices that way. There's no blind spot, some invertible matrix that you're never going to get if you just keep multiplying elementary matrices. And instead of multiplying elementary matrices, you can just start with identity and do elementary row operations. That's the same as multiplying elementary matrices. So one among other things, what this theorem says is that any invertible matrix in the world is one that you get from identity matrix by doing elementary row operations. Now, if you do just one elementary row operation, you get an elementary matrix. But if you do more, you get more complicated things. But that's what the world of invertible matrices is. This is the end of this lecture, and I will see you in the next lecture.